Hi, good morning, everyone. I'm Dong Liu from Yale University, and this is a joint work with Yan Xuan from Columbia. Today, I will be presenting our system, GraphSnapShot, and it's a system accelerates graph machine learning in large scale and for better storage, caching, and the systematic design. So you can also find our code and experiments on GitHub at the link below. So our background and motivation is the large graph neural network also suffer from two fundamental issues. And the first one is neighbor explosion problem. And when we do the sampling work, let's say do k-hop sampling, we go tap k-hop neighbors and the number of nodes grows exponentially. And this leading to the memory and the computational overhead. And the second issue is IO inefficiency. So many frameworks currently resample neighborhoods at every training step. So it will trigger repeated random disk access and GPU stalls. And our goals is very simple but impactful. So the problem of our work is, can we design a system that builds a graph layout once and use the adaptive caching to serve future queries efficiently? And here is our system overview. And our system combines two core components, and the first is SEMHS. It's a slab-encoded multi-hop storage mechanism for disk-efficient layouts. And the second is GraphSD sampler. It's a dynamic multi-level caching controller, and the architecture is structured in 3 layers. The first one is we split the graph into dense and sparse regions, and then we build SEMH slabs sorted by the hop count, and then finally we deploy a multi-tier cache system, and from the GPU memory to SSD. And this architecture gives both of us structured disk access and a flexible memory reuse. And the diagram also shows how data flows work across disk, DRAM, and the GPU memory during the training. And here we go to the SEMHS. It's a slab-encoded multi-hop storage, and it's efficient. The idea of it is to pre-compute the key hop neighbors and store them in separate disk partitions or slabs. And it's denoted as mathematical D to mathematical D1 to DK. So for many nodes, if we want its H hop neighbors, we just let's look at the H number slab. And here is we also give the upper bound of the SEMHS computation. And this means that each node is guaranteed to access the most 1 block per hop and with the upper bound guaranteed time. And here is the algorithm of it. So the algorithm is basically three basic ideas. Firstly, we sort all edges by the source node ID, and for each hop, we recompute the H hop neighbors and store them in a dedicated slab. And these slabs are pre-allocated continuously and on SSD for faster sequential rate. And this turns on structure neighborhood sampling into a predictable slab rates. And the following is refresh policy for the GraphSD sampler. And once we store the graph efficiently, we also need to cache them smartly. So this is why we designed GraphSD sampler. And we have a few underlying realization of this. And firstly, for each cache tier, we will maintain a cached neighborhood and estimate how skewed it is to using a parameter that adaptively learning to fine-tuning on. And we define an adaptive refresh rate as the formula here, and then we use the cache update equation to combine our adaptive cache with the disk fetch cache, so we can maintain a trade-off cache for the best performance. And then for the cache update, we use a multi-layer caching, and the L0 is on GPU. It's the smallest but the fastest. And the L1 is larger but moderately fast. And the L2 is on SSD. It's slower, but it has a full coverage. It has a larger storage. So let's be intuitive perspective. The hot nodes stay close to the GPU, while colder ones are demoted out but still available on some slower resources like SSD. And the multi-level designs ensures high cache hit rate with minimal memory usage. And here we came to the end-to-end latency bound. And now let's put them together. So we model the total latency per minute batch at this algorithm. So our system maintains GPU throughput while minimizing the host memory, and we can reduce the first two term of this formula significantly. And here is we came to the experimental part, and we test different cache strategies. And our best configuration on-the-fly selection with shared cache, it has the best performance. It achieved over 30% reduction in training time and the highest cache hit rate and the lowest I/O latency. And this confirms that both dynamic selection and shared caching are key to efficiency. So we also have a optimization across different data set for the experiment. So we do a comparison on OTB benchmark archive products and Mac. They have a compression rate significantly. And we also do accuracy job experiment, and it shows that the accuracy job is almost nothing, so almost zero. So it also proves the efficiency of our system. And here we also do a method comparison across different systems, and it also shows that our GraphSnapShot has better accuracy, GPU usage, I/O latency, and cache hit rate compared to some original methods like GraphSnapShot, like PUIG cluster loader or Quiver. So this also shows our efficiency of our system. And we also do our experiments on the dynamic graph, and it shows that our cache hit rate is very large, and it can reduce the memory and accelerates the training and the inference process significantly. So our conclusion is drawn here. To summarize, our GraphSnapShot system introduced a storage-aware and cache-efficient system for graph training, and it provides fast slapped trees, disk access. It also adapts caching based on the workload and the stateless. So in the future, we plan to explore stream-based graphs and deeper JNNs and a large-scale graph system and a scenario. So we can also do some hierarchical partitions adding in this system. We are exciting for this, and we are exciting to do some intersection between industry and academic. Thank you for listening, and I'm very happy to take questions of you. Thank you.